Welcome to this update on SuperGen ORE Hub Workstream 4. This presentation summarises the progress made on design events at the University of Plymouth and University of Oxford. Through Workstream 4, we are investigating whether design events are an efficient alternative to the traditional design process for ultimate limit state calculations in floating ORE. For context, the traditional approach involves simulation of multiple seeds of fixed duration for given met ocean conditions. This is typically the equivalent of 18 hours of full-scale data for survival scenarios. The peak responses are then identified in the data, allowing the calculation of an extreme value distribution, which provides the probability of a response magnitude not being exceeded in a short-term exposure to the specified met ocean conditions. A characteristic response is often characterized by choosing a high percentile value, ensuring there is a low probability of exceedance. Alternatively, the largest event in each seed can be averaged to provide a typical extreme response, which is the typical approach we use to provide a benchmark for our design event analysis. The traditional approach is relatively straightforward, but is time-consuming given the large number of scenarios which must be considered in the design process, particularly in the early stages where the design may be iterated. Design events are a potential alternative approach which target the extreme response using specific short duration profiles. We typically refer to these as short design waves for wave-only applications and short design events for combined wind and wave applications. There are multiple existing methods to formulate design wave profiles. For example, you could use the average shape of the largest waves, known as nu wave, or the average shape of the steepest waves, referred to as most likely steepest waves. Through SuperGen, we are primarily focusing on a response condition approach, known as most likely extreme response, or MLER, which accounts for the linear response of the device using the RAO. We consider each design event profile in two forms: single and constrained. A single short design event is deterministic and the profile is considered in isolation. In a constrained short design event, the target profile is embedded in a short background wave. This is stochastic and requires multiple seeds to be run. Our primary aim is to determine whether these design events can reliably be used for the design of floating ORE using the traditional approach as a benchmark. We now move on to an update on our floating offshore wind design event work. We are primarily using a real-time hybrid physical modelling approach to avoid issues relating to different scaling laws for the floater and wind turbines. In this approach, we represent the aerodynamics using a thruster system controlled by a feedback loop involving the motion of the platform and a surrogate model trained using OpenFast. In previous years, we have demonstrated the system using a 1 in 70th scale Voltern US semi-submersible platform. This year, we have developed and tested two additional platforms, a 1 in 70th scale spar platform for a 15 megawatt turbine based on the Windcrete design, and a 1 in 62 scale semi-sub for a 10 megawatt turbine. The spar and Voltern US models have both been updated to include a tower that closely matches the natural frequency of the full-scale equivalent. Load cells have been integrated into the base of the tower. This allows us to extend our design event approach to tower-based bending moment and improves nacelle acceleration by allowing high-frequency oscillations to be captured. The hardware and software of the aerodynamic system has also been updated. These updates improve the communication time between components, leading to faster response of the system. The new spar model has been tested with the combined wind and wave setup. A cutout speed scenario has been added to the analysis to go with the parked and operational scenarios considered previously. Focusing on the response condition design events, the single approach performed well in the sea states where the turbine was operating and the responses were wind-driven. For responses with significant high-frequency components due to the tower response, such as tower-based bending moments and nacelle acceleration, a constrained design event approach is required. Further work is needed to incorporate high-order loading into the selection of background waves. Preliminary tests with the new semi-sub model have been conducted in a parked scenario and compared with existing data with the Volta in US. For the Volta in US, the predictions from the constrained design waves were typically within 5 to 10% of the target value, with response conditioning demonstrated as beneficial for this parked scenario. The new semi-sub also compares well with the traditional approach, although pitch was less well captured than for the Volta in US, which requires further investigation. We will be thoroughly testing the combined wind-wave approach for both semi-subs over the next year. Preliminary tests with the Volta in US platform were promising, and we hope to report back positively next year. Moving on to the wave energy applications, we have continued our collaboration with Motion Energy. The irregular sea state data collected through the traditional approach provided some interesting observations. The hog angle of the device and mooring load were both subject to infrequent and considerably larger extreme events. This was evident in the extreme value distribution, which exhibited a long tail. This indicates large uncertainty, even using the traditional approach. The cause of the large events appears to be linked with waves that are near breaking as they interact with the device, with dependence on the position of wave breaking behind the device. This leads to a characteristic wave profile that features a steep front and back-sided wave, which is similar to that seen for the other two-part hinged wave energy converters we have considered previously. When considering the design waves, we found that a single design wave was generally sufficient to achieve the traditional approach benchmark. However, response conditioning was found to be of relatively low importance in this application, indicating that the linear response is not a dominant factor. Steepness conditioned waves seem to be the most promising approach, although tuning of the focus point of the wave was required to avoid premature breaking. For mooring load, constrained new wave is also an option, which provided significantly larger responses than seen in the irregular data in some scenarios. The infrequency of the events means that the traditional approach may not capture the largest extremes, increasing the value in a design event approach for this application. Naturally, this does mean that the likeliness of occurrence is low in reality, but it is considered beneficial for the developer to be aware of the potential for significant exceedance of the design load. A method based on shifting the focus location of steep waves to achieve breaking at a particular location does seem to offer an option to the developer, which may be particularly useful during the early design stage to inform design choices. Over the next year, we intend to explore the combined wind-wave short design event approach with more devices, including the existing semi-sub model and a tension leg platform. We will be looking to bring together all evidence gathered to date to provide recommendations for short design event application in future recommended practice documents. On the wave energy side, given the similarities observed in the wave profile for the other two-part hinged WECs, we will be exploring the parameter space for the steepness conditioned approach in the future work. We will also be exploring background wave seed selection processes to improve constrained approach agreement. Thank you for listening to this update. If you would like any further information, then please get in touch using the details on screen now.